Hello everyone. In this video, we are going to look at the formulas for damping coefficient and spring constant that you constantly see in vibrations, right? So when we have this mass spring damper system and we attach to the mass a spring and a damper, you might wonder, what are the values for this K and C in an actual physical spring or damper, right? So spring is like basically a metal with some diameter D that is wound around some shaft with diameter capital D, and the material has a shear modulus of G, and N is the number of active coils. So if it has N coils, then what is the formula for the spring constant? If you watch one of my videos under playlist machine design, you see from the book Shickley, I showed you this formula. So this is the spring constant for a compression spring. And as I said, in this formula, N here is the number of active coils. Capital D is the coil diameter, small d is the wire diameter, and G is the shear modulus. Okay, so this is for a spring constant. Now, for calculating the damper constant or damping constant or coefficient, that needs a little bit more calculation. So here, let's say we have the cylinder filled with oil and viscous fluid, and this object here is the piston, and it has a radius r. The radius of the piston is r plus h, where h is the gap between them, and the pressure gradient across the two sides of this piston, so the pressure drop across this is a partial of p with respect to g. The length of this piston is L also, and it is moving with velocity v or speed v inside the viscous fluid, and we want to find the damping coefficient here. So here we have some assumptions. So the piston diameters are R and L. The gap between piston and cylinder H is quite a bit smaller than R. The piston velocity is V. Flow is steady, fully developed, laminar, and incompressible. So that means the rho is, of course, constant in this case. And the three components of the velocity of any particle, which, by the way, here we use the cylindrical coordinate. There is a Vz, there is a Vr, and there is a V theta. And the only component that is non-zero is Vz, and Z here is the axial direction. So Vr and V theta are both zero, and Vz is not a function of Z or theta, it's only a function of R, and clearly not a function of time, because this is steady state flow. Okay, and of course on the boundaries there is no slip condition. What does that mean? It means that here, basically, at this boundary here, if you look at this volume of the oil, at this point here, Vz should be equal to this V, the velocity of the piston, and at this point, Vz should be zero because the cylinder is fixed. Okay, so we have no slip boundary condition. So here we have to use Navier-Stokes equations, and we used it in cylindrical coordinates. We look at the z direction. In the z direction, this is the Navier-Stokes. There are a few other terms on the left which are depending, and on the right that are the functions of theta, but here nothing is a function of theta. There is no spinning. So all of those theta terms are zero, and even in this simplified version of it, there are some other terms that are zero, because V of z is only a function of r, not z, so this term is zero, and V of z is not time variable, so that term is zero. And the other thing that you have here is, again, second derivative of v with respect to z, this term is zero. So basically all you have is mu times this 2, if you take that partial to the other side, equals partial of P with respect to Z. Now since it's a pressure drop, this guy is a negative, so we set it equal to negative G, where G is a constant in this case, and this G is a positive number. Okay, so instead of writing partial of P with respect to Z back to back, we just use constant G. Okay, so our notations are a little bit shorter. So if we divide this negative G by mu, the negative G over mu is going to be this guy here. And this one, you can also write it as 1 over R partial with respect to R of R partial of VZ with respect to R. So you can write it like this. Okay, so now we multiply both sides by R. So we get this one on the right-hand side. On the left-hand side, we have this. Of course, we have to integrate it to get this. So we integrate it with respect to R. And this is a linear function, so you get a quadratic function plus a constant. Now we divide both sides by this R. So this partial of V with respect to VZ with respect to R is going to be, if you simplify one R, you get a linear function. Here you get a hyperbolic function. So that is partial of V with respect to R, and this is some very important thing that we have to come back to it. Okay, now if you want V itself, you integrate one more time with respect to R. This is going to be a quadratic function. That hyperbolic is going to be a natural log and plus a constant. So you have two constants to find. So you apply the two boundary conditions at R equal capital R. V of Z is V, and at R plus H, which is the inside of the cylinder, the radius of the cylinder, V should be 0. So you get these two equations, and what we care about really is C1. So we just subtract the two equations and solve for C1. And if you do, you are going to get C1 to be this. Now, why is this C1 important? Because we are needing it in this partial derivative. Okay. So now why C2 is not important? Because the next step we need to do is to find the shear stress due to viscosity. If the fluid is Newtonian, tau shear stress is mu, where that is the viscosity, times partial of V with respect to R. Now here you can write it as full derivative because V is only a function of R. And of course, this partial is exactly what I told you that we need. It's this guy here. So we are going to directly plug it in here. And that is that term. If you multiply by mu, you are going to get this. Now you see in the tau, C2 plays no role, only C1 does. So now that's tau. Now what is the force exerted by the fluid on the piston? Well, on the piston, the only place that the force is applied is on the surface of it. So at this point. And this location corresponds to R equal R. So only on the outer surface of the piston, R equal R, is where you have that shear force. So what we need to calculate is the shear stress at that location, tau at R equal R, and multiplied by the surface of that piston. And surface of the piston is 2 pi R over L. So if we multiply these together, we are going to get the shear force, okay? And that is exactly what we are doing here. So now in this tau formula, which is a function of R, wherever we see R, we plug in capital R. And we multiply by the area of the piston. Now we bring in R inside the parentheses, simplify, you get an R squared and a constant. And then whatever C1 that we had earlier, we are going to plug it right here, okay? And that is this guy there. Okay, so now here we use the assumption that H was way less than R. If H is way less than R, what's going to happen? Okay, so this is F that you had originally. Now what happens? Well, between these two terms inside parentheses, this is a small term squared. This is a small term times a bigger term. So this one is way bigger than that one. So here we neglect this in comparison to 2RH when we only keep 2RH here. And for this natural log, if you know natural log of 1 plus x is basically x minus x squared over 2 plus dot dot dot, correct? If we only use a linear term because x is very small and neglect higher order terms, we can use this approximation. Now, in this case, 1 plus x is equal to r over r plus h. From here, you can see that x is basically negative h over r plus h. So this guy here, this natural log of that, could be only approximated by x, which is this, and that is what you can see over here. Also, in this denominator between r and h, you know, r is much bigger than h, so here we can neglect that comparison to h, so we just keep r. Good. So you see here are all of those simplifications that we do. And now here I bring this r to the numerator, multiply a negative by everything, and I simplify it one step further. And then basically multiply the mu by everything, divide by h, and I get this. Now here you have two identical terms that would cancel. And if you simplify, finally, your friction force, your viscous friction force is going to be negative 2 pi L mu R V over H. Now for a damper, for a viscous damper, we always say that the damper force is negative C. C is the constant of it times V. V is the velocity. So if we say these two terms are equal, correct? These two are equal. From here you solve for C, and guess what? You get this beautiful formula. 2 pi L mu R over H. That is the damping coefficient for this configuration. And as you can see, C is proportional to mu. So the bigger the viscosity, the same order, the bigger the C. C is also proportional to R. A bigger piston means a bigger C, and also proportional to L. A longer piston means bigger, linearly proportional, bigger C, and C is proportional to 1 over H. So the smaller gap, the bigger the C is, okay? So that formula is extremely important and very simple in looking, and we derived everything from Navier-Stokes equation. So that was a practice for you on your fluid mechanics, basically. So hopefully this video was useful to you. You ended up with two nice formulas here, correct? One of them is this one, that is for K, right? And the other one is this one for C. So one is this, and the other one is this one that you can see right here. Okay, so you got two nice formulas, and hopefully you can use them in your applications. Thank you so much for your attention. I'll see you in the next video.